Good morning, actually good afternoon everybody, and welcome to this lesson on three-dimensional digitization. With pleasure, today I introduce Carlo Bayod that will talk about online presentation and visualization methods, visualization of digital content, and will show several case studies. Both of projects of Factum Foundation. I remember to all attendees that Bayod is project manager at Factum Foundation, and the lesson then will continue with a workshop as said before on Stereo-photometric recording. And so Jorge, Cano, and Julian Matthews will explain and show this innovative method of recording. I welcome Carlos, and I remember to everybody that your questions are very welcome, both written in English or Italian or in Spanish. And you can type them in the chat, both on Zoom and YouTube, or you can raise your hand and ask to talk. Third, I remember also that soon the lessons that we are listening will be public. At the end of the course, they will be public on the Fondazione Cini YouTube channel, and also will be shared with you and with all our public in the complete version. Since some of you noticed that the first and the second lesson of this course have been some problem in the YouTube streaming, and so the streaming on YouTube lack of some minutes at the beginning. In the next future, we will add the complete version after the course will finish. So I leave the floor to Carlos, and I thank you again for being here.
Thank you, Costanza. Can you hear me well?
Yes, very well.
Thank you for the introduction, and thank you everyone for attending. This is going to be the third workshop or the third practical session that we are going to be doing in this course on 3D digitization. And I will share my screen now. Can you see the first title, right?
First slide, yeah.
So just to put a little bit of context, in the previous sessions, we have been focused on the aspects of recording and reproduction. So we have been looking at different methods for capturing surface and volumetric information, employing mainly the Lucida 3D scanner for the surface of paintings, for example, or for the flat objects that have interesting texture. And then we were also looking at photogrammetry, especially close range photogrammetry, for capturing other types of objects like architectural elements, sculptures, things that are fully three-dimensional. And then we were able to compare the different systems that especially we are researching and applying in the Factum Foundation work. We were also looking at ways of reproducing that digital information back into the physical world. So this physical output is part of what we believe is essential for a digital approach to cultural heritage preservation. For us, making facsimiles is a way of demonstrating the quality of the data that were captured. But today I want to focus on this aspect of a digital output that is ways of communicating and making accessible the information that we are capturing to a wider audience through remote access online. And this is also a very important part of the work that we do in the Factum Foundation. So the first part, it's going to be about reviewing different ways of presenting information online. I'm talking about high resolution 3D data that could be disseminated and shared remotely. And the second part of the session, it's going to be mostly about practical demonstration of a new recording methodology that we are researching and developing in the Factum Foundation. This is going to be something that my colleagues Jorge Cano and Julian Matthews are going to be explaining today. And this new method is called Stereo-photometric recording. It's a new approach to surface 3D scanning, and it's going to be something that will have a lot of importance for our work and to many other projects that will be happening related to the high resolution capturing of data. But that will be in the second part of the session. It's going to be a live demonstration, so we will be able to show you how we prepare the system and how we do an actual recording of a small object. But the first part, as I say, it's going to be about how to disseminate information. So when we do facsimiles, we believe it's important in order to help the conservation and research of original objects, original works of art, original elements of cultural heritage in general. But the dissemination, that is how to make the different information accessible to the public or accessible to users broadly, it's also essential to the activities that the foundation is doing. I'm going to be talking today about the remote access to surface data, and specifically online and interactive ways of communicating surface data in high resolution. We developed a specific way to make this possible. So in the Factum Foundation, by understanding works of arts as complex subjects, we are interested on this idea of multi-layered information. So for example, when we are talking about the surface of a painting, we understand that the way a painting looks now is the result of an accumulation of layers in history that is the result of the different hands that have been actually modifying it because of restoration, because of repair, also the layer of time, the way it has been aging over time. So this idea of layers of information is also something that can be described through actual layers in the way you present a painting in a digital form. So I will show you exactly how we understand this way of communicating works of art. The idea of a multi-layer browser or a multi-layer viewer that can give you a very unique and very privileged access to the historic trajectory of a painting or any other surface through the computer screen. And in order to do that, I want to show our multi-layer browser also in comparison with other ways of viewers that are accessible, made by other museums, other organizations that are interesting in one way or another, because it tells you about how people understand works of art and where are other people applying their notions of what is important to communicate in a painting. I'm going to be talking about mainly surface, so not 3D shape, because if you remember in the previous session, we were showing other applications, for example, like this platform called Sketchfab that allows to upload and share 3D models, for example, that you have captured with photogrammetry or any other 3D scanning systems. But today I want to focus on something that in a way it has its own difficulties and its own complexity, which is how can you show this complex relation between the color and the texture of a surface. and how to show 3D data, or in other words, how to show depth and relief in the flat screen of your computer or your tablet or your phone, it's a complex subject because it requires to take a series of decisions, aesthetic decisions, but also about how you are going to illuminate virtually your relief in order to highlight certain features instead of the others, or how can you play with transparency between layers in order to show one aspect or the other. So there are ways of showing information, and I'm going to be talking specifically about paintings now. And one good example of how this ways of communicating the 2D data of a painting is, for example, what they were doing in a team in the Rijksmuseum directed by Robert Erdmann around the Bosch Project. And this is something that I believe you can see this homepage now. Yes, right? You can see it.
Yes, we can see it.
So this is the project website. This is not a Factum project. This is the Bosch Project. And what it does is they created like this database of the different paintings by Hieronymus Bosch. And it allows public access to some information, some technical information about paintings. For example, this one in the Galleria dell'Accademia in Venice. And it's showing information that is usually only available to conservators or to the museum technicians, because it's going to be showing not only the visible color information, but also other layers that are actually behind the visible layer of the painting, which is, for example, X-rays or infrared, ultraviolet, etc. The way this application works, and I hope you can see it on screen on real time as I'm doing it now, it's that you can actually navigate through a painting in high resolution. You can focus on a detail, and then through the mouse, you can actually move this series of 4 images that are actually moving with the mouse as I move it on top of the screen, in order to show different layers of painting in a very intuitive way. So it is possible to see, for example, the full painting as the visible color, the way it's normally obtained with color photography. But then it is also possible to see it before and after a cleaning process or a restoration process. So as I move this curtain, because effectively it's like if I was unveiling a curtain of information, it is possible to see it before and after, as well as other layers, for example, the infrared before and after, or with different frequencies. So focusing on a specific detail, you can change the view mode that you are interested to see. This is based on the idea that you are always looking at a point in a painting, either in one layer or the other. You cannot see in this type of visualization the same detail with 2 layers at the same time. So either you are seeing color or you are seeing infrared photography, for example, or either you are seeing it before or after, but never at the same time. So it's a decision that was taken when designing this method of browser, and it was working, and it is working for communicating these paintings that otherwise it would be necessary to, let's say, download all these images that are usually very high resolution images that are heavy for usual computers. So through browsers like this, it's a very effective way of communicating this type of information. But as I'm saying, it only allows to look at the same detail with one layer or the other, or in this case, one of the 4 possible layers. This type of information is only showing 2D data. That means that all of these paintings were never recorded with 3D scanning methodologies. It was about showing different flat layers of information. When we want to incorporate 3D information, and this is also something that in fact we've been researching a lot, we decided to create this type of multi-layer browser, which I'm going to give you a small example here. We developed this for the data we captured of Tutankhamun, the 4 walls of the funerary chamber of Tutankhamun. So it was allowing to visualize the different layers in combination or independently. So in this type of browser, it was in fact possible to see the same detail at the same time because the screen was divided in 2. And this is just a different way, another way of understanding how this information can be communicated. But it gives, especially because in this case we are talking about 3D scanning information, it gives the opportunity of looking at the relief without the layer of the color. It gives the option of looking at the relief as if you had lift and remove the layer of color, but not to see through the painting, not to see like the layers underneath. It's just a way of turning on and off the different layers depending on what you want to be looking at. So the way this browser, this multi-layer application was working, is, and I'm doing it just live now, is through a link that you can access with a certain password if it's not public. And then, for example, the north wall of the funerary chamber of Tutankhamun, it is possible to look at the color in high resolution. You can get close to it. This was captured by the Factum Foundation back in 2009 with composite photography. And then the 3D scanning, it is something that you can visualize, for example, in combination with the color. So you are seeing at the same time relief and color information, but also you can look at the relief without the color. And this is one of the real advantages of being able to look at relief information from your screen. You can inspect the wall without the distraction of the color. And this allows you to look at details specific to this part of the wall. It is by looking at this information that it's been in our website for years that, for example, the researcher and Egyptologist Nicholas Reeves was actually demonstrating his hypothesis that the actual north wall in Tutankhamun was initially containing an opening, like a door, maybe leading to a hidden chamber that was maybe closed while making the tomb for Tutankhamun. So it is by the possibility of looking at the information without the color that he believed that there might be traces or clues that could lead to the possibility of having a hidden chamber behind the known space in the tomb of Tutankhamun. And it is, again, thanks to the possibility of looking at 3D information without the need of downloading very complicated software or having super powerful computers. It is just by using shaded renders of the 3D information that you can communicate relief data as if it was an image. And this is one of the great advantages of this type of multi-layer browsers. So as you can see, what I'm doing is I'm navigating in parallel to the plane of the wall. And this is the same way as we do when we are using this type of applications for understanding a painting. We are never, let's say, rotating the plane of the information. We are always looking at it in parallel, and it's another decision that was taken in order to communicate this information. But there are other ways of showing the 3D information of a painting that actually understands it as if it was a sculpture. I mean, something that you could actually rotate and turn the inclination in order to look it better. For example, when they were recording, this was another project, not by Factum, but it was made back in 2015, when they were recording the painting Alchemy by Pollock in the Peggy Guggenheim Museum in Venice. So what they were doing in this project was using structured light scanning systems to capture the relief of the painting. In this case, as you know, with a painting by Pollock, this is something that actually contains a lot of information in the relief and in the texture. This is a short video that was done by the team in charge of this project. It's showing the viewer, the online viewer that they created to communicate the information of the painting. It was possible also to turn on and off the layer of color, but then it was also possible to turn the painting and rotate it a little bit, as if it was something that you can inspect the same way as you are looking at a sculpture. This is exactly this type of movement that I'm talking about. It's not just a parallel navigation, it is something that you can rotate. Actually very similar to the way Sketchfab works for showing a 3D model of a sculpture, for example. You can rotate the painting like this, and then it was also possible, as part of the tools in this browser, to move the direction of the light. The same way as you could be working with a physical reproduction and you were moving the raking light. This is the browser. This is the viewer here. I hope you will see it in a second. And as I am actually navigating through it, I can rotate the painting like this. And this was another way of understanding how these objects can be communicated. In a way, it could be considered, and maybe in my point of view, it is something that is not very, let's say, coherent with the way you look at a painting, because it's not like something you can, when you are looking at a painting, you cannot really rotate it like this, especially if it's a big format. But it's interesting, especially with such a sculptural painting like this one, with such information in the texture, what can be done in terms of playing with the light. So with a tool like this one, it is possible to decide the direction of this virtual light that is helping you to look at certain details that you are interested on. So I can look at the same area with light from different directions, more raking, more perpendicular, etc. If you have any comment or question, or if you have seen previous examples of things like this with the Pollock, for example, please feel free to comment. And then going into this way of showing 3D information of paintings online, the way that this company Hyrox are doing to show the capabilities of their ultra high resolution 3D scanner, it's also very interesting and is worth mentioning here, because the way they are doing it, it's also through this way of being able to rotate the 3D information as if you were looking at a sculptural object or a volumetric object.
My name is Emilien Leonard from Hyrox Europe. I was invited to participate to the Girl in a Spotlight project initiated by Abby van Divere. The technical examination of Vermeer's masterpiece, The Girl with the Pearl Earring, took place at the Mauritshuis Museum in Den Haag in March 2018. For this project, we specifically designed a new motorized XYZ scanning system to perform a scan of the full painting in high resolution with the Hyrox microscope. And now we are waiting for the girl to come. You can see the setup. And the special stands. Everything is ready to go. I think the girl is coming as we speak now. The goal of the inspection was to learn more about Vermeer's painting technique, to evaluate the surface condition, measure cracks and topography of various key areas while assessing past restorations. With this equipment, my colleague Vincent Sabatier and I made the first 10 billion pixel panorama. Overnight, 9,100 multifocus 3D files were automatically captured and then combined in one single panorama where 1 pixel equals 4.4 microns. Here, for example, we concentrate on a double dot on her shirt placed by Vermeer to add texture in the fabrics. Start point and then go up to here.
I wanted more of the lines.
Black.
Yeah, there we go.
Like here somewhere?
Yeah,
or I can go even lower.
That's great.
Okay, end points.
Yeah, please.
And then I will use a bigger magnification at 140x. Alright, so we'll have a good 3D information. And this is the bottom point, and this is the somewhere here will be the top point. So you will do 30 single files.
Wow.
The Hyrox software is then automatically moving the lens up and down with very high precision, capturing a series of images at different focus and combining them in one fully focused image. The motorized XY stage is then moving to the next position, creating a high-resolution panorama. In total, 10 key areas were captured as all-in-focus super high resolution to create 3D stitch of those surfaces where 1 pixel equals 1.1 micron. This is the result of this scan, a 3D image of the surface where we can observe with high precision the topography and measure the height of those two dots. Here the color represents the altitude. Red is the highest and blue is the lowest point of this 3D. You can also see cracks, dust and pigments. The total height is 130 micron, which is 1/7 of a millimeter. We just developed a panorama website to give you access to the full scan and zoom directly in a painting. You can also open and zoom further in a 10 high-resolution key areas with up to 1 micron resolution. If you click on a 3D logo, you will open a 3D viewer that lets you manipulate those high-resolution 3D stitching and experience the girl in a completely new way, including a virtual spotlight. It's as if you have the painting in your hands. You will find more information about 3D digital microscopy on our website.
Okay, so what I wanted to actually mention of this Hyrox technology is the way that they are making their information available online, and the kind of viewer, sorry, I will connect here. The kind of viewer they created to show the information of this particular painting. So this scanner that they were testing in this video, it can be considered actually a microscopic 3D scanner, and it is capable of capturing color information and also relief data by this technique of focus stacking. So it's about getting some kind of relief information by calculating the distance between two shots taken with different focus distances. So it is obviously something that can provide this impressive level of resolution as a 2D image, as a color image. But then the way they are actually showing the 3D information is similar to the previous Pollock example I was showing. It is possible to, in this case, not the full painting, but just a small fragment, and then rotate it in different directions as you zoom in or out, and then you can decide what is the inclination that you want to use to see the information, and then also to manipulate the light direction. But this method, it's actually something that, at least with the current state of this technology, it will not be possible to actually have the full painting with this same level of resolution. What you are seeing on the screen is just this example of the eye of the girl. We can also, for example, look here at the pearl earring. And this is just a section, small sample of 2 by 2 centimeters. It is obviously super high resolution. So, for example, if you remember when we were talking about the Lucida scanner, we were obtaining 1 pixel of information every 100 microns. In this case, it is possible, according to what Hyrox are claiming, to get to 1 micron per pixel. That's 100 more resolution than the Lucida scanner. But this is something that you can actually obtain in almost in laboratory conditions, with the painting placed in a specific position, with this limitation in terms of the maximum area that you can capture. And it's something that, as small samples, could be interesting if you want to focus on specific points in a painting. But as a way to understand the full conservation state of a work of art, it is still something that is not practical in, let's say, as part of a real project. This way of visualizing information, that is combining the topographic information with the color, it's also allowing other ways of visualization in terms of assigning different color to the altitudes in this 3D model. And also, if you remember what we were mentioning about looking at things without the color texture as a way to really understand the level of resolution they have, well, in a case like this, is truly something that could be considered ultra high resolution for art applications like this one.
Carlos, sorry, I interrupt just to comment one thing that maybe it's obvious, but well, this of the Hyrox technology is really impressive, of course. But as you said before, many times probably, there are choices to make in order to express what the research is about. And for example, the example of the Guggenheim, so the Jackson Pollock alchemy that you showed before, it was possible to how do you say, to see these results, to see this the recording of the painting in real life at the exhibition. There was a room entirely dedicated to facsimiles of alchemy, and it was really useful to understand a painting as complex as this. There was this entire room. I think did you visit it? Were you here in Venice at the time?
No, I did not. I have not seen it.
Well, probably some of our audience was here, and the room dedicated to the facsimiles of the painting was yeah, really useful to understand the dynamics and the structure that maybe with color in the real painting you have an idea, and then seeing the relief of the facsimiles is very different, very useful for.
Absolutely. No, at the end, I think the best is the combination of different ways of showing information. So it's not about choosing one way of explaining an original. It's the experience is usually more rich and more interesting if you are combining different ways. If you are maybe combining digital access with physical reproductions of the digital information. And the exhibition that you are mentioning, it's a good example of that, because they were not limiting to one way of showing the information. Once they have captured the data with 3D scanning technologies and with the color recording, they were experimenting with different visualization methods. So the whole idea of understanding the complexity of a painting like this one, it emerges as infinite possibilities. And you are right, it's a good example.
Yeah, it's also the good example could be the exhibition that Factum Foundation made in Bologna last year. No, actually now it's 2 years ago, almost. So it's the combination of the digital presentation visualization of the 3D models, and then also the facsimiles in real life.
Exactly, no, and also as part of explaining an original object. So in exhibitions when you have the possibility of showing an original, it could be a good idea to have, besides to have nearby in the same room, the same space, maybe different other ways of explaining that original object through physical facsimiles or through digital viewers like these ones I'm sharing today. So it's not about making the choice between, okay, am I showing the original object, or I am showing just other types of reproductions. So I think the more these techniques are becoming available, it is more important to show them in combination with the original, in the same room, in the same space, or as part of the same exhibition.
When I was saying that it's necessary to make choices, I was referring more to the Hyrox technology. So I meant that when it comes to digitizing or make a study, at that point maybe you have to choose which technology to use depending on what you're looking for and which kind of artifact or heritage you have in front of you. So, yeah.
Exactly. I mean, it's about selecting the right technique for the type of information you are looking for. If you are interested in measuring at a micron level differences in height in certain brush strokes or certain aspects of the craquelure of a painting to a microscopic level almost, you might be interested in technology like Hyrox. Knowing also the limitations, which is in terms of size or in terms of maybe stitching together or aligning together different local captures to compose a final panorama. I will show you now an example in which in which 3D scanning and color recording technology was actually applied to not a small section of 2 by 2 centimeters, or not to just one painting, but to a collection of paintings. I already mentioned before in the previous session the work that the Factum Foundation was doing with the Raphael cartoons at the Victoria and Albert Museum. So this is a section in the website of the museum. And with the information that Factum captured, they created these viewers that are actually showing the color, and then you can turn the infrared information also recorded as part of the project. And then for the first time, a museum was showing in their website the 3D scanning of a full collection or a full series of paintings, not just one example, but the pioneering project that the VNA was putting together in collaboration with Factum was this idea of having making accessible the huge area of the cartoons by Raphael in an online viewer with the possibility of understanding the texture from the computer screen or from any device. And as you can see here, they are using the same visualization method as the first Bosch project, is this curtain mode that you have to see either one, the same detail either under one type of layer or the other, but never at the same time.
Can I ask you if it's a combination of, well, I guess many type of software, let's say, but it's AAAF protocol, the way it zooms, it seems to be, if you know.
Could you repeat that? Sorry.
Yeah, I'm sorry. Does this software, does this visualization method uses the AAAF protocol?
Yeah, exactly. You're right.
Combined
with the Mirador platform. And because at the end, the 3D information that we are showing and that the VNA is showing is nothing but an image. So at the end, there is a lot of work to be done in terms of showing 3D information, or let's say ways of sharing 3D models as part of a AAAF protocol. As of now, the most effective way that I know is to show images, and you can combine different layers. You can make all sorts of comparison between images, but at the end, these renders are nothing but shaded images, the same way as if it was talking about color or infrared. So the same type of information, but using the multi-layer browser that Factum developed is something that it allows you to actually see the same detail. This is the same as the Tutankhamun example I was showing before. You can divide the screen in two and look at the same detail, both with two layers at the same time, having, for example, color on the left and just relief on the right. And then another option is the possibility of combining layers together. So for instance, I can have color and relief on the left, and then infrared photography and relief on the right. So as a tool for conservators to actually study the preservation state of a work of art like this one, it has enormous possibilities, because it's like if you were in front of the painting without the glazing, without the protection glass that it has, and being able to look so closely to any detail, also as if you were having a raking light illumination, raking lighting.
Plus, since it's AAAF, you can use also the annotation tool, so it's even more useful.
Yeah.
There is a question from Elena Tardio that asks, I don't know if it's pertinent or not, but I would like to ask something about the archival implication of facsimiles. Are they archived, and in case, how can they be archived?
Archives in terms of the storage of information, or archives of the physical facsimiles?
I think she means the physical facsimiles.
So the way that, at least from our experience, the way that we have been working in Factum is that we are creating, when we make a facsimile, we make it for one specific goal, for one specific commission, for one exhibition, or some specific program by a museum. Is something that is done for one particular use, and normally we just make one unit of it. It has actually a relative value by itself. In a way, the facsimile is the byproduct of the fact of having digital information of the object. The real valuable info, I think, is the actual digital data that can be archived and can be used to help the preservation of the object in the future. The facsimile itself, it's made with, let's say, economic materials. It's something that could be made a second time if it was necessary. But the real difference is having the high resolution data or not. And also in terms of archiving the digital information and the right of the stored information, the way we are always doing it in the Factum Foundation is very clear. So all the information that we captured with our systems belongs to the owner of the original artwork. So all the current rights or future rights over that information, we believe that it should stay with the museum or with the institution that owns the original object. And this is very clear for us because we are never keeping any right of use over the data we record. We believe it should belong to the owner of the physical original object, because this way, any profit that could have in the future, it should be in a way reinvested in the long-term preservation of the original. We believe that this should be in a way a sustainable activity, so that the advantages of having digitally recorded objects should in a way bring more good even to the actual preservation of the original. And with that, we are very clear on that. If you were referring to something different, just let me know.
Thank you.
So just to conclude, I want to show, based on this idea of the multi-layer browser that was developed in Factum and that we have been actually improving over the years, there are some very specific applications that can be extended out of the possibility of looking at paintings as a stacking of layers of data. It has the possibility, for example, in a case like this, to observe the same object with a different combination of layers. But also, it gives a chance of having in the same place different objects that are in a way scattered in different museums or in different places, and for the first time can be seen together thanks to a browser like this one. The case of the Politico Grifoni that I have mentioned before is a good example of that, because the 16 panels that are surviving from this polyptych, which is from the end of the 15th century, are now in different museums. Like the central panel of St. Vincent is in the National Gallery in London. These two side panels are in Brera in Milano, and then they are also in Washington, in Paris, in the Vatican, etc. So one way of looking at them all together, and also with the possibility of comparing between each other, is through this type of browsing application. So it is possible to inspect each of these panels in 3D and color from the same, in the same application with the same link, and then you can play around with the layers of data exactly and looking at them in detail as if you were in front of the original. So it gives this advantage of looking, for example, at the predella that is in the Vatican, in the Pinacoteca Vaticana, with the color, with the relief, and then you can maybe turn off the color and look only to the texture of the panel, in this case recorded before a restoration process, so you could see the actual state of the surface. But then you can go and look at the other panels. For example, you can then immediately go and look at the panel in London and compare that there is such a difference in terms of the restoration treatments that it's been having over the recent history. You can look at the combination of color and relief, and then you can inspect again the relief on its own without the color distraction, and spend your time, comparing, especially if you know what you're looking for. If you are interested on reading specific features on these physical objects, you can do it through this browser from the same application and from the computer screen. It gives also the possibility, for example, of incorporating layers that are different stages in the restoration process. The panels in Brera, which are representing St. Peter and St. John the Baptist, we have the opportunity of recording them before and after a restoration process. So the 3D information, we could incorporate it into the same browser so that one extra layer is the what happened before and after this restoration process that happened in 2016. So you can compare exactly what was fixed and how the texture changed because of this treatment. And then, of course, you can incorporate more layers of data. We have been talking mostly about color and relief. So for this big painting by Murillo that we recorded in Seville, in Spain, we carried out the color recording and the surface scanning with the Lucida scanner. You can see the very subtle details on the canvas texture, but then the conservation department that they were in charge, they were also facilitating us the X-ray and the ultraviolet layers that we could register and incorporate to the layers. So at the end, it's all about making sure that each detail in one layer is corresponding to another detail, to the same detail in another layer. It is possible, for example, to see, ultraviolet and relief at the same time, or looking at what happens when you combine X-ray with a bit of transparent color or X-ray with relief. So for any part of the painting that has lost its original painting and has been reintegrated or repainted, it is possible to understand what is the change in texture that has been happening because of that. So it is possible to increase the amount of layers that you incorporate, and this has no limitation really. So for a painting like this one as well, it has very different texture to the Murillo example I was just showing. The Black Square by Malevich, the first one of the series that he did in 1915. It is possible to see it also without the color to appreciate this interesting texture that has been acquiring over time, this very specific craquelure. And because of the X-ray information that was provided to us by the Tretiakov gallery, you could see what was actually underneath the black square. So on the right, you have just the color information, and on the left, you can see what was actually underneath the black square that was painted that made this work of art remarkable and very famous as an example of this moment in art history. But it is also possible to understand what was the painting that was actually below. So this idea of combining visible layers and not visible layers, it's also something that you can do with browsers like this one. And again, for us, because it's part of what we do, and this is part of how we understand the objects that surround us, having the layer of the relief is essentially important. It's not just about showing flat layers of information. It's about making visible this three-dimensional quality of the canvas paintings. We were mentioning before this idea of incorporating annotations by conservators, incorporating the notes and maybe comments on the painting. This is also something that's possible to be done as part of these extra layers of information that can be captured. Different hypotheses, different research elements can be added onto it, up to a point that even, for example, it is possible to include what is called a damage map. This is this famous Epiphania cartoon by Michelangelo in the British Museum. So the restorer was drafting this super interesting, like a conservation report of the object that when you place it on top of the 3D information, it makes complete sense. You can actually relate every aspect that was annotated by the conservator with its correspondent feature on the texture. And of course, when you are combining color, relief, and the damage map, this is where you really get to understand the object with all the layers of information. So, as you could see, the dissemination of the digital data is an essential part of how we understand digital preservation. It's not just about the recording and making facsimiles. It's also about what are the decisions that you take to communicate this information to the public. And this is one thing that I wanted to share today, all these examples of online remote access to the information in high resolution. And I would like now to introduce this other system that I want to share with you, which is the photometric stereo recording. But I would like to ask you if you have any questions or comments about the things that I mentioned so far. If not, I will just move on to making a very quick introduction to the system that my colleagues Jorge and Julian will explain in a minute. The photometric stereo recording is a new methodology that in the Factum Foundation have been working on it for a few years now. And it's just about trying to find another way of capturing surface data through digital color information. It's based, as it will be explained in a moment, by generating relief information out of taking color photographs with different light directions, and then because of the shadows, because of interpreting the different illumination of the image of the same area, it is possible to extract some relief information. The advantage of a system like this, in comparison, for example, with the Lucida scanner, is that we are talking about something that works faster than the recording that is carried out with a Lucida system, for example. It can obtain at the same time relief and color information, whereas with the Lucida scanner, we have to do it just with different systems and then making the registration in the post-processing phase. And then it's also something that provides higher resolution. We are mentioning that the Lucida scanner is having a 100 micron resolution. In this case, we are capable of going to 4 times better resolution. So instead of 100, we can get closer to 25 microns just by using one of the cameras that we have in Factum. But actually, you can even achieve higher resolution if you wanted, just with better equipment. We will be showing in a moment how this system works, and we will be showing it by recording a section of this object, which we will also explain in a minute. What I will be doing now is I will make a very brief break, very short break of just a couple minutes, so we can prepare the setup, and we will come back to you in a moment with this live demonstration of the scanning. If that's okay with you, Constanza.
Sure. Let's prepare and see you soon.
See you in a couple of minutes. Thank you.
Yeah, just a few minutes. Like the picture that we take.
I will take a few minutes. So we can continue now. Can you hear me?
Yes, very well.
Yep. So here we have my colleague Jorge Cano and Julian Matthews. Maybe he will mute in a minute. So this is Julian, and Jorge will be explaining this system of the photometric stereo recording. Jorge has been part of the team in charge of developing the Lucida scanner. So he's been part of the Factum Foundation for years. So everything related to the software development of the scanner, as well as other research and development projects in the Factum Foundation. He's one of the engineers that has been instrumental to make them possible. Julian is a recent addition to the team, also an engineer, and he's becoming more important every day in the different projects that we have involved in the new technological developments in Factum. So I will leave them explaining you this system, and we will try to make a live demonstration of how it works by recording a section of this object, what we call the standard board. This is something that we have also created in Factum, and they will explain why this object is important to many of the projects that we develop here. So I will put myself in mute, and I will leave them to talk from now.
Great.
Okay.
Thank you, Carlos.
Thank you, Carlos. Thank you, everyone in Italy. Made this happen. I'm Jorge, and Well, first, I'm going to explain the difference between photogrammetry and photometric stereo, just because I'm sure that everyone here knows about photogrammetry, and I think it's a good method to introduce the technique called photometric stereo and to understand it better. No? In photogrammetry, which here in Factum Foundation we use a lot when we need to scan objects and huge volumes. As you know, we keep the object obviously in place without movement, and we take the camera and take pictures, different pictures, while moving the camera. In this way, we can get a data set with a lot of pictures with the object with different viewpoints. In this way, a computer now, in the past, the calculation was done manually, but now we move the folder with all the images, and as I said, the computer with trigonometric and triangulation methods calculates 3D positions for each vertex on the object. So, as you can see, we need several pictures of the same object to reconstruct the 3D geometry of the object. In this case, with this setup that you can see here now, is more or less similar. We have a camera, the object, and we are going to take several pictures of the same object, but instead of moving the camera, we keep both the camera and the object in the same place, and we will move the lights. In fact, we are not going to move the lights, but we are going to switch on and off sequentially 4 lights that we have in this position.
Why would you use one over the other? And in fact, we often use both in the same projects. Do you want to explain why we would do that?
With photometric stereo, we are going, we start to use this technique. We started development, the research like 3 or 4 years ago, but this year is the first one that we are starting to use in projects. Most of the time, photogrammetry works great with when you have to scan a volume, like an object with different shapes. If you look from here or from here, it has different shapes, so you have a volume. But photometric stereo is great when we have to scan more or less flat surfaces like that. I mean, paintings, bas reliefs, this kind of objects. So, and on the other side, the other question, at some point, it's a very good idea to merge both techniques in the same projects, because with photogrammetry, you can get great quantitative results. You can get precise coordinates with centimeters or millimeters, but it misses many details of the surface. So the idea is to merge both techniques, photogrammetry and photometric stereo, to get the best of both worlds.
So a combination of quantitative and qualitative data. And I know that Carlos mentioned this during his lecture, but he had also mentioned sort of the differences between using this photometric stereo technique and using Lucida. Mm-hmm. Do you want to discuss a bit from your point of view the differences between the two from a technical point of view, and how we use both of those differently and together at Factum?
More or less the same. We are using, at this point, we are using both systems, because both are great for very tiny details on surfaces. But in terms of resolution, for example, with Lucida, we can go up to 254 dpi per inch, mm-hmm. which is very nice. But with this methodology, we can go, in this case, with this lens and this camera, depends on the sensor and the lens, but we can go to up to 700 dpi. So, and also one great advantage of this technique is that we can get also the color, both the 3D and the color. So,
so does Lucida have any advantages over the photometric stereo?
Yeah, because photometric stereo needs at some point needs to get the scale of the object, and Lucida does a great job with that.
So in many ways, too, Lucida is actually more quantitative.
Yeah, we can say same as photogrammetry.
By the way. Sure.
Quantitative results, qualitative results, and merge both good results.
Great.
Yeah.
Should we start talking a bit about the technical components of
yeah, I'm going to talk about the general overview of the system. We have 4 lights here, custom units done in Factum. Then we have Canon, yes, air camera with a 50mm lens, and also we have a microcontroller with some custom circuitry, optocoupler, and some other components. And I can go to show you some details on the different parts that I.
Maybe let's start with the light.
Yeah, let's go start with the internal parts.
This is something that was made right here in Factum, right?
Yeah, exactly. For example, this is the perfect case to talk about how things are done most of the times here in Factum. In this case, for one of the development, one of the scanners that we did like 4 or 5 years ago, the Veronica scanner that can record faces, human faces in a very short time with very detailed. We take like 96 pictures of the objects in 4 seconds. So we need very fast flashes that can recover in a fast way. So we didn't found nothing in the market. So we developed our own system. We bought these xenon lamps, and then we. In fact, Manuel Franquelo designed this custom PCB to allow this faster response of the flashes. So we design the PCBs, we produce the PCBs. Also, we design these CAD pieces, and also we print them. So in this case, we can build the entire flash unit, integrating technologies from different places.
And here it is in full. And while we're on the topic of the lights, why do we use 4 lights? Why not 8? Why not 2?
Yeah. This is a good question, and it's related to it's something in between quality and fast post-processing, and also to not get a lot of thousands of pictures. So you increase the post-processing time, and also the need of information. No, you need more images, so more information to post-process. In the past, we started, the first prototype was used 4 lights. Then we passed to a prototype with 40 lights in a hemisphere. And now we decided to go with this because we both get good results in terms of resolution, and also we can process to 20 centimeters by 20 centimeters, an area of 20 by 20 in a few minutes. So it's, for now, it's perfect for our purposes. using just 4 lights and 4 images. And also, with just 4 lights, at some point we can create different sequences. For example, we can, instead of switch on and off independently the lights, we can switch on by pairing. So 1, 2, 3, and 4. In this way, with just 4 lights, we can play with different groups. We can get more lights if we need it, for example.
Great.
Regarding the lights, I think is more or less done. Then the system uses a microcontroller, as you know, to play the sequence of triggering the camera and its light. So here we can see, we can't see because it's covered by this PCB, but here is an Arduino Uno.
We have another one over here.
Yeah,
we can talk a bit about that after.
Yeah,
but maybe
later you can tell us about microcontrollers. Just to finish with the circuitry, here we have an optocoupler to avoid damage. I mean, we are mixing both signals, different voltage from the USB, from the computer. The camera has a different power supply, different voltage level. So to avoid damage anything, we are using an optocoupler in this case, with this in mind. So yeah, here we have some.
Yeah, these are 3 different types of microcontrollers. The one that we're using for this project is an Arduino Uno. Arduino actually being an Italian microcontroller company. I'd say it's probably the most common one. This Uno one in particular, the most common one that exists on the market, but they have several other models, including this one right here, which is the Mega 2560. More recently, they've also come out with a lot of IoT devices, which essentially allowed sensors to connect and exchange data with other devices through the internet or Bluetooth. Another example is a company that produces them called Raspberry Pi. They're slightly different. They're more microprocessors, being the heart of a computer rather than an embedded system of sensors and whatnot. And for example, here this is the what Jorge has in his hand is the controller box for the Lucida, which also has down here an Arduino Uno, as you might be able to just see down there. I know it's not too clear, but yeah, Lucida runs completely using this microcontroller as well.
Yeah.
And maybe to go over, just to show quickly on sort of the software side of things.
Yeah, when you have a microcontroller, you have the electronic parts, the hardware, but you have to write also the software, which in this case is the firmware. In this case, we can see the firmware of the Arduino that the photometric stereo setup has inside. It's very simple. It's just a sequence of lighting on and off the different lights.
Very simple.
Well, maybe not so simple, but it's simple. Basically, switch on and off the different digital ports of the microcontroller. So each of the lights has 2 wires, and it can receive a signal from the microcontroller, and it can the capacitor release its energy on the xenon lamp, and the flash unit leads the object. So each one of the flashlights has 1 line for the microcontroller, and the sequence is very simple. It's just we trigger the camera, which simply the shutter will open to get the light inside the sensor, and at the same time, more or less the same time, we have to adjust the timing for that to get good results. It switch on the light, and the picture is taken.
Great. And last and not least, you want to say a couple of words about the lens that we're using?
Yeah, as I mentioned before, in this case, we're using a 50mm lens, which works well, great for this kind of distance and object. As I mentioned before, we can change the lens. We can use a wide angle lens or 100mm lens. In this case, we use 50mm, which allow us to record this surface with a lot of detail. And also the distance between the object and the camera stay something that is affordable in a small room. Usually the digitalizations, you can't go with a huge setup, so it is good to get a light setup like this one. And regarding the setup, I think is more or less clear. We can go with
let's maybe discuss a bit what this standard board is, which is something that's very important to what we do here in Factum.
Yeah, this standard board is very important for us because it was designed to be difficult to scan. No? When we start to use a new scanner, the first thing to do is scan this board. It has 3 sections, one with reliefs. In fact, this is a facsimile of a section of an Egyptian relief with all the cracks and this kind of stuff. Then we have a cracked area with very tiny and small cracks, and also different circles with different tones, black, gray, completely white. But to go worse for the scanners, we have different glossy on the surfaces. For example, here is medium glossy. This circle is the most difficult part to be scanned because it's both black and glossy. So most of the scanner can't see anything in this area. And in this last section, we are mixing both colors, cracks, and different glossy surface varnishes. So.
And I know you mentioned this a bit with the lens, but right now this is a certain distance from the board.
Yeah, in this case, between the object and the camera, there are 45 centimeters, which is the minimum distance with this lens. It needs this distance to focus the object. So this is why we are at this distance.
But as you were saying earlier too, with the different lens, we would also be able to capture something
exactly
bigger, smaller, depending, and shoot it from a different distance.
Depending on the object, we can change the optics to get, or if we need not so much detail, so we can go with a wider lens.
Mm-hmm.
Or if we need more detail, we can go with a tele lens and get more details.
Yeah, great.
I think we can go with the first scanning.
Yeah, should we give it a go?
So first, we have to set up the camera, the parameters of the image, like the ISO and the shutter speed. I'm going to use 50 for the shutter speed, 100 for the ISO, and the sweet spot for the diaphragm or the f-stop of the lens. Then let's focus the object to get a sharp image. Now we are ready. And as I said before, I'm not going to press the buttons on the camera because we have the Arduino, the customer electronics. So the microcontroller is waiting for a character.
That we sent through the serial port.
Exactly. It's listening to the serial port. And when I press the sequence starts, so we are going now with this flash, then
you can see the results on there.
This one.
And then next is this one.
The next one.
Yeah.
So as you can see, maybe we can see the different images. At the end, we have different lighting from top, right, bottom, and left.
Yep.
So when we finish with one section, we go for the next one. Now I'm going to move the object because it's a test object. Obviously, when we are scanning a painting or historical and something with more value than this one, the idea is to move the scanner instead of the object. So one of the next steps for the next prototype, we can show the X and Y idea. This is the frame
for the Lucida.
Of Lucida, exactly, with some stepper motors. We have two Y-axis and one motor for the X-axis. So in this way, the microcontroller, one more time, can manage everything. So we can go very precise way from one point to the next one. So this for the next year. Now I'm going to scan the next part of the object. And one more time, let's play the sequence. As we can see, there is some time in between pictures. This is needed to store each picture inside the SD card, inside the camera. One of the next possible solutions to do that and to achieve a faster scanning system is to connect the camera to the computer and tethering do the tether of the images. In this way, we don't need to play with the SD card and so. So now we have the images inside the SD card, and the next thing to do to finish with this scanning is to switch on the camera, get the SD card with the images, and
process them.
Exactly.
Great. So I will, while they go and take the data for processing that Jorge will show you in a minute, I will show you in my screen a good example of the type of information we are capturing. So I will give a couple of minutes for Jorge to prepare the information that he will be sharing on his screen in a minute. You can see my screen now, right?
Yes, we do.
Okay, so this is just a few examples of different objects we were recording before. This is one type of information we are trying to improve thanks to the this system of photometric stereo recording. This is an example of just a paper with text written by hand. And this is the way it looked when it was recorded with the Lucida scanner. You can see there is a bit of noise in the information. This is before any processing, before any editing of the data. But the same object recorded with the photometric system, it is showing more definition in the data. It is being possible even to understand the relief of the areas that are not visible on the lower part of the image with the Lucida scanner. You can see that the top line of text is visible with both systems. It is only cleaner and more focused. It looks like more focused just because it is working with higher resolution levels. And what is important for us and for many future research projects is that even the part that has been very softly incised with incisions on the paper are in a way possible to read thanks to the photometric system. This is the same data but exaggerated in the relief, like increasing the contrast in order to exaggerate the relief, so it becomes even more visible. So for research projects that are all about trying to read things that have lost ink, for example, trying to detect incisions in a surface, it is possible to use a system like this one. These are other methods of visuals that are showing even more evident this information. So now Jorge will show on his screen more or less what would be an introduction to the process of working with the information that he captured, how he could actually obtain and work with 3D information from the color photographs that he was capturing.
Okay, I'm going to share my screen. Okay, is working?
Yes.
Can you see? Okay, great. Yeah, I'm going to show you the post-processing of the images that we record previously. In this case, for the post-processing, same. We have several ways to do it using the same technique, photometric stereo, but we decide to go with a very simple workflow that everyone can use. In this case, we are using a commercial software called Substance 3D Designer from Adobe. Recently bought Adobe bought it, but we are in different setups. We, for example, use MATLAB, which is more, I mean, we can go in more detail with the results. But let's go with this workflow. I have here the images from the standard board. Previously, I used Lightroom in this case to pass from the raw format to GPJ. So I'm going to open. Well, I'm going to show you first the different images because we saw from on the camera, and here you can see much better how the picture looks with the different illuminations. As you can see, same position, different lighting. So the idea is to go pixel by pixel, estimating how the surface is orientated to the camera. So let's open the images. The order is important for the calculation. So Now, I create this workflow previously to go faster, but it's very, very easy. This software works connecting different nodes, so you can drag and drop this line and connect from the input images to the post-processing nodes. So first, I'm going to show you how from these input images with all the shadows, the different shadows from the different lights directions, we can estimate the albedo, which is the color without any shadow, which is very important when you work doing facsimiles or including if you are working on the video game industry. Sometimes you need the color of the object without any shadows to create the shadows, to recreate the shadows virtually. So in this way, as you can see, no shadows in the image. So apart from the 3D estimation and the surface, with this technique, this is very important. We can also get the color of the image. Let's go with the 3D, which is the topic of today. And let's connect every input image to this node. Now it's processing, and when ready, the first step is what we call the normal map. This is the basic, the basis of this technique. Everything is supported by this. Here, for each channel of a RGB image, the information of the angle of the surface is stored in the red, green, and blue channel. So in this way, we can integrate through different paths on the image and get the 3D data. So here, as you can see, this is important. Normally when we think on 3D data, we imagine vertices connected by lines and this kind of stuff. But most of our work, we use polygonal vertices and this kind of 3D. But most of the time we work with 2.5D images, which is a depth map like this one. We store inside the structure of an image the values of the height of each pixel. In this way, we can move and calculate and make analysis on images faster than if we work with vertices and 3D numbers for each point. And also, when we have the 3D data, we can make analysis on this surface. For example, in this case, we can separate the low frequency data from the high frequency data. As you can see here, we can get the overall shape of the object, and here we get the small details of the surface. This is very helpful for us because we can use, for example, if we want to materialize this object, we can use different techniques for the materialization. For example, we could use the low frequency height map to be milled on, for example, polyurethano or whatever, and we can 3D print, but only in a small surface of thickness
of 1 or 2 millimeters, and then join both objects together to get the overall shape of the object. When we have the 3D data here on the depth map, on the height map, we can save the data. So I'm going to save the color data without shadows. And then we can open in different software. Most of the time we use GIS software to work with this kind of data. I'm going to open the depth map. Here it is. And as I mentioned before, one of the nice characteristic of this system is that we get both the 3D and the color aligned at the pixel precision. So, for example, in this case, we have in 2 layers, as Carlos showed us in his presentation, with different. With the zoom menu, I missed some of my icons, so I couldn't show you. Sorry. Here we go. Okay. Now we can see how each tiny detail is aligned in both the 3D layer and the color layer. And also we can view the surface in 3D with all the details. Let's hide the color information. For example, with photogrammetry, it is, let's say, not impossible, but very, very difficult to get this kind of details if not using this technique. Here we are looking at maybe 2 centimeters by 2 centimeters. There are a lot of points of information. Just to compare, I'm going to open the same object. Here we can see the standard board. This is Lucida data. As you can see, really nice details. But if we superpose the data from photometric stereo, we can go more in we can see more details. And we are discussing about Lucida, photogrammetry, photometric stereo. It's not the work. I mean, the question is that the best is to get the best of each technique. It's not one or another. The best is to use to merge different techniques to get the best results while scanning. I'm going to show you the last example with a different surface. In this case, is copper plate with a small scratch, and this is the color. And I'm going to show you with Lucida. Let's measure, for example, this small bump. As you can see, we are talking about 300 microns of details. And let's switch on the photometric stereo layer. As you can see, we can see details that in Lucida it's completely invisible. Here we can see a comparison of both surfaces. And this kind of software is also great because we can go with detail, take measurements, compare surfaces, and do analysis with more details than with the other software. So I think it's more or less clear how we can use photometric stereo to improve the digitalizations. I don't know if we have any questions on that.
I have a question, maybe also other people will have, but I start with mine, and it's more a curiosity. Is this software that we are seeing, I don't read very well, global mapper, I don't read it well. Is it, it's not made by Factum, I guess?
No.
Is it taken from medical, biomedical?
Yeah, it's people use, I mean, it's a software of is geographical information systems for maps and this kind of data. We use two softwares. One is Global Mapper, which is a commercial one, but most of the time, and we did a lot of developments the last 2 or 3 years. But mostly my colleague Enrique Esteban, in an open source GIS software, which is GRASS. I'm going to open it. And this is the other software. It's very similar. You have the data, the images that you can load and make analysis and this. But I would like to show you, for example, this add-on was developed by us, by Factum Foundation, to work on depth maps. First was only for Lucida, but now we use this software and also basically this add-on to, for example, as you can see, always, most of the time, the objects are bigger than the area that the scanner can take in one shot. So we have to scan in different sections. It's not a simple problem to merge these surfaces. So we develop systems to align these different areas in both X, Y, and Z, and create only one surface. Imagine, for example, with Lucida, I don't know, maybe Carlos can tell us better, but one of the biggest canvas that we, or paintings that we scanned was the Rafael, sorry, Carlos, could you?
Yeah, the Rafael cartoon.
The Rafael cartoon, and it was
that's probably the biggest area we recorded.
5 meters by 3.5 or something like that.
In terms of a single work of art, yes. Then when we are recording the walls of the tomb of Seti I, that's hundreds of square meters.
Mm-hmm. Mm. So for that case, we developed this add-on to more or less automatize the process of merging all the data. Most of the time we get problems with the scanning, with noise, and so we develop some tools for filtering and analysis of the data.
One of the important tools that Jorge mentioned quickly earlier is this difference between topography and texture, or in other words, what we can consider high frequency relief and low frequency relief. So it's, in a way, how we can extract the skin of something, which contains every texture detail, and have it separately from the shape, from the topography. There is no one single way of understanding this. It's not an objective value above which something is high frequency or below which something is low frequency. It just depends on the object or the project. But it's very useful sometimes to be able to work only with the texture relief or working only with the shape of things for visualizing, for rematerialization as a facsimile. This is something we are constantly doing, this difference between what is the shape of things and what is the skin and the texture of things.
Is there a rate of error calculated, or is it possible to calculate it, or not really?
Sorry, could you repeat the error?
The rate of error, a percentage of error, is if it's calculated or there's no error.
No, always when you get a measurement, you have errors. In photometric stereo, we didn't know yet. We are, and it's it's a complex issue, one about the errors, because there are precision, there are a lot of things to have in mind. But for example, with Lucida, we are always take measurements with less than 100 microns on resolution on the Z axis. And with photometric stereo, in the X and Y axis, we can go below 20 microns. So the errors are around these numbers, not much.
Then there is also this idea of how close it is to the real surface of the object. So right now on screen, you can see actually this cross-cut comparing the Lucida information with the same area captured with the photometric recording. The photometric recording, which is something that we are actually developing now, works fantastically for local information. Jorge will tell me if I'm right, but then it needs to have this complement of the Lucida scanner or photogrammetry or any other measurement system to have like a system of references to which the photometric information can be registered or can be adapted to, because there are some variations in the ramps or slopes in the data that could be understood not correctly by the photometric. So for details, it's looking perfect. And then when it's combined with other 3D scannings, it's even better, you know. So this is where we are at this moment.
Thank you very much. I don't read any question for now. I invite again people to ask something if they have an urge to do it.
Now or never?
Now or never? No. We can give another possibility. So we have a question.
There's a question here.
Yes. Elena asks, well, a question about the first part of the class. I was wondering if the 2D or 3D images we say could be used to make art accessible to people with disabilities. Maybe
Okay,
I read
so,
it.
yeah, I'm reading it. So these things I was showing is basically to show the information visually on screen. This is important for remote access. So yes, it could be something that making works of art more accessible to remote places or to people who don't have access to actually visit the original in a museum. So this could be an answer. So it is making something accessible in that sense. When you don't have the opportunity to visit something physically, you really need to get used to these other ways of online visits if you want to get close to a work of art. And in those cases, it's important to be able to see beyond the actual flat image of the color. You actually get to see the real object, how it works, when you have the possibility of understanding the texture. This is basically what all this course is about. And then, of course, there are other ways of disabilities that, thanks to rematerializations of texture, it could convert visual objects into tactile objects. You can get to touch a work of art once you have recorded it in 3D, and thanks to reproductions of them as physical forms. So there are, I don't know, two examples that come to my head when as an answer to these questions. But obviously there are many other ways that we haven't talked about yet, which is all the possibilities of mixed realities, you know, virtual reality, augmented reality, different ways of accessing 3D information and making, you know, immersive environments for cultural heritage uses. And this is also something that we will be discussing in the next class, other ways of employing other engines, other like video games engine to approach and make accessible high resolution information from remote access.
Thank you. Yes, in fact, Elena was specifying that she was thinking about the visually impaired people, so with the facsimiles, but what you...
There is something that we are always very interested about, which is, you know, in museums, there have been previous examples of making, let's say, famous paintings accessible, you know, for the blind. No? So it's about making something that you can, I don't know, the Mona Lisa, for example, you make the face and the figure as something in volume. Okay, so that's one way of doing it. If you want to actually make a tactile experience out of reading the figure, there are other ways, because, for example, when you are working with tone and relief, you can, for example, create a physical reproduction of the areas of light and shadow in a painting. And this is a different approach, which could be also interesting. Imagine, I don't know, a Vermeer painting or any other, or a Caravaggio painting. It's not so much about making visible the figure, it's about making visible the areas of light and shadow. And this is something you can recreate through depth, through relief, but also maybe playing with the texture, with areas that are more soft or more rough. So there's a lot of possibilities between this relation between tone and relief.
Thank you very much.
Thank you.
I think that if you don't have anything more to add, we can say goodbye and see you next lesson. That will be the 18th of November. Thank you very much to Jorge, Carlos, and also Julian that I don't see now, but I know is in the same room or very close to you.
Well, thank you, Costanza, for your help, and thank you everyone for attending. See you in the next class.
Thank you.
Bye-bye.